I'm good. How does the Orgo look to you today?
It looks fine, but I did just find out, so there's a lot more people than normal enrolling in Orgo this year at my college.
Yeah.
So, um, okay, because then the person who made this textbook is an instructor at NYU, and they're no longer my instructor. I don't know who my new instructor is, but I'm pretty sure that means I'm not using the same textbook because only this Orgo teacher is the one using the textbook now.
Okay.
So,
Well, from what we did, it wouldn't make any difference because it's so basic. But going
yeah.
forward, there would be a difference. Is it possible to find out what book you'll be using?
Right, like on my college website where you enroll for classes, it'll like say the instructor, but if they don't know who the instructor is yet, it'll just say staff. And right now mine just says staff, so I don't know who it's gonna be.
Okay. So, but you're saying that the book is related to the teacher, and if you don't know the teacher, you don't know the book. Is that what you're saying?
Yeah, and I know for a fact I won't get this professor because the same time that my Orgo class is at, he's teaching another Orgo class. So I can't have him. Yeah.
Okay, well, in that case, using this book doesn't make any difference, although it's not my favorite book, and we could switch if you want. The reason it's not my favorite book is it explains things in complicated ways. They're not wrong, but they may not benefit you as much as another book. So here's what I have sent you. I sent you two books to do practice problems in. The easier book is called Klein, and the harder book is Brucey, but they're both very good books. So if you like one of them better than what we're using, you can look at the same material, see how it's handled. Then we could switch to that book.
I might prefer that because when I was doing the practice questions from this book, some of the questions were worded horribly.
Yeah, well, I got to the opinion that I didn't like this book very quickly.
Yeah,
Um,
I asked other kids who had this textbook and they said they hated it and they always used other books throughout the year.
okay, well, I'll tell you what. Um, I think Brucey is a great book, but Klein is the easy book. And if we don't know what you're going to get, easier is easier to learn, and then you can go up a notch. So I would recommend the Brucey book, the Klein book, which I happen to have here. So what do you say we switch to that? And then if we know what your book is, we'll switch to that.
Okay.
Okay. So let me go over here and let's see who is. I think Eric is it. Yeah, that's it. Okay. So we'll load that up. Okay. Yeah, there it is. Okay, perfect. Pull that in there. Okay, it's slow because it's a big book. And all right. So let's see where we would be. Okay, acids and base were coming up. And we've done all of this stuff here. Okay, so I know where we are now with Klein. So we're going to be starting up. We'll look at molecular representations to see if we need to talk about it much, but that's where we are.
Okay.
And here is where we were. So what I'd like for you to help me with are these questions, because this kind of covers everything important from last time.
Okay.
So here we have, it's an ion, so there's a charge here. And the first thing I want to know is what the total number of lone pairs are.
8.
Okay, I got to do this. I don't know, there might be more. So the total number of lone pairs on the entire molecule.
Because wouldn't it be 3 on each of the 2 bottom oxygens and then 2 on the top
Okay,
oxygen?
let me just do this one here. Okay. Yeah, you might be right. You might be right. I didn't figure it out, but I think you're right. Yeah. I just thought, wow, that doesn't sound right, but you're right. Okay. There's 6 here. Yeah. Absolutely correct. Okay. So you get 1 point for that one.
Okay.
Very good. How about the formal charges?
Of each of the atoms?
Yeah.
The bottom two oxygen, -1 for each
Yeah,
of them.
that's good.
The top oxygen is 0,
Perfect.
and the nitrogen is +1.
Okay. You're going to be my favorite student. Okay. Total charge.
-1.
Very good. Okay. And, you know, I'm an optometrist. And when I say, he goes, better or worse? And I go, this one's better. He goes, very good. And I think, what did I do? But you're doing something better than me. Okay. But, you know, he goes, very good. So, okay. How about the bond angles?
Is it 120 for
Yeah, it's
all of them?
120 all the way around. Yeah. Yep. How about the hybridization of all the atoms? Each one.
It's like not like the whole thing is sp2.
Yeah, it is.
Yeah.
That's the
Is that what you mean?
sp2 of the nitrogen.
Yeah.
The oxygens,
Isn't
they,
it just S?
okay, let's not talk about the hybridization of the oxygens yet, because there's something I needed to tell you, and I haven't told you that yet. I'm going to tell you immediately after we're done with this. So let's not bother with the hybridization of the oxygens just yet,
Okay.
because there's an exception to a rule. Okay, how many resonance forms do you think we have here?
There's a total of 3.
Yeah, we do have 3. So basically, what would happen is it would be like that. I'm doing it quickly, but you understand it. Perfect. Okay. Okay, number of sigma bonds.
3.
Yep. Number of pi bonds.
1.
You're amazing. Okay. Okay. And then, okay, this is the last one. You get to win $100 million if you get this one right. How many anti-bonding orbitals?
Is there 4?
Yeah. Okay. So here's the thing. Normally when I do this, nobody ever gets them all right. And you're the first person that's ever done this.
Yeah.
That's really impressive. Yeah. So that's really impressive. Okay. Very, very good. Let's, there's no reason to go over this other than that one exception I need to tell you about. Okay. So what happens with hybridization is that you want to have the most stable molecular form you can. And it's not just based on Vesper. So Vesper is the most common way to do it. But for orgo, whenever there is resonance, resonance will win out over Vesper. It will win out every time for your course. Higher level orgos, maybe not. But for this course, always. So what that means is that normally if we had something like this, we would say, oh, that's going to be sp3. Because what happens is when you do that set thing, you have 1, 2, 3,
yeah.
and then 4, right? But what happens is this. If you have an atom over here, an atom over here, an atom over here, and then there's a lone pair like this, couple bonds, whatever, here, and you compare it to this, so it's a really simple case. What's going to happen is that this over here we know is sp3, and that's because of Vesper. But because of resonance winning out over Vesper, this is going to be sp2, because sp2 allows this to be in a p orbital, and it allows you to have a situation where you can have resonance. So resonance will win. So the structure that we're talking about is this. Whenever you have that, this is going to be sp2. And if it's a single bond like that, it's going to be sp3, and that's it.
Okay.
So that made sense, the rule?
So if there's a double bond at all, it becomes sp2? I mean, yeah, sp2?
Well, if there's a, okay, there have to be electrons here. So there was something I did last time. I was looking through it. We were talking about allylic. So what happens is when you have this goes a little bit beyond what we're talking about, this or this. This is going to be allylic and it's going to have resonance. And when you have resonance, it's going to be all sp2, the entire part that has resonance. So all of these guys and then all of this is going to be sp2.
Okay.
Now carbocations are O as sp2. Radicals are O as sp2. So those really don't change. But carbanions, when you have a lone pair on carbon, that's the one that makes a difference. And it also makes a difference like this. If I put an oxygen here with a lone pair and I compare it to this, one of these oxygens, either the top or the bottom, is going to be sp2. Can you guess which one will be sp2?
Is it the top one?
Yeah, sp2. Can you tell me the reason why it will be sp2? The answer is, I'm sorry, give you a chance.
I was just gonna say, yeah,
Yeah.
something to do with resonance, yeah.
Right. So you don't actually need to understand it, but it's kind of cool to know that the molecule is competing between Vesper and resonance for stability. And resonance makes it more stable. So even though the bond angles are not as good as they would have been, the resonance stability is better.
Mm-hmm.
So that's how it works. And this is how Orgo works. Orgo is a bunch of rules that get broken and you memorize the exceptions.
Okay.
That's just how I mean, that's why I like Orgo and that's why a lot of people hate it. So
Okay.
it just depends on what you're into. Okay. Let's see what they have here. Okay. So I'm working, so you have a copy of the link to this book. The book I'm working with is Klein. And let me see what they're going to do. Okay. So basically, they're going to do something like this. I mean, this whole section is really about this. So I'm going to make a lot of weird stuff here. Now, you might already know this, but every end of the road, every bend, so I'm thinking of it like a road, and every, oh, there's another, oh, that's not a bend. Yeah, I'm good. And every intersection has a carbon when you draw it like this, intersection, and this will be an intersection, yeah. That should make sense. Does it?
Mm-hmm.
Okay. So let's test you. We're going to give you a cyclohexane molecule. I know it's easy, but how many carbons are there here?
7.
You got it. While we're doing this, just to reinforce an idea, I don't think we've talked yet about something called degree of unsaturation. And they're going to talk about that somewhere in here. And this molecule here is a good example for doing this. So if you have an alkane, you're going to have all single bonds. That's what an alkane is. And it's going to have the formula CX H2X plus 2. So that's the formula for an alkane. Now, if you have an alkane with 7 carbons, not a cycloalkane, but an alkane, that would be C7, H14, and then that would be plus 2. So that would be C7H16. But if there's a ring, we're going to call it a cycloalkane. And what happens is, in order to close the ring, we have to remove 2 hydrogens. So the formula for a cycloalkane is CxH2x. So this will be C7H14. And it turns out that if you have an alkene has 1 CC double bond. And it turns out that we have to remove 2 hydrogens to make that double bond. So this will also have the same structural formula, CxH2x. So if it was a 7-carbon alkene, we could do something fancy like this. We could go 2, 3, 4, 5, 6, 7, put the double bond there. C7H14 would be the molecular formula for this. And if you want, we could basically go CxH2x plus 2, CxH2x, and then CxH2x minus 2. And what happens is this would just be an alkane. This would be a cycloalkane, or it would be an alkene like this. And this structure here could be an alkyne. So what's happening is we're going to make the rule that for every ring or pi bond, so this has 2 pi bonds here. For every ring or pi bond, we're going to lose 2 hydrogens from the alkane formula. So this is because of 2 pi bonds that it's going to have this formula here. And this is because of 1 ring or 1 pi bond. And then this is because of the lack of any of them. So if we wanted to, we could say that in the same category, we'll make it a different color for fun, we could have something like this. This would also have this formula because it has 1 pi bond and 1 ring. So that's how that would work.
Okay.
Does that make any sense?
Yeah, I think so.
Now, later on in the course, unless this book deals with it earlier, we're going to learn more about this. We're going to come up with a formula for any compound. And we won't have to be doing it this way. We'll have a fancy way to do it. But normally they don't deal with that yet. So we're going to just say this is good enough. And we're sort of just giving you little pieces of information that will be used later. Okay. You have no problem identifying lone pairs. Let me see if I can make this slower. Page display. Okay, that'll do it. Yeah, good. Okay, and let's make this bigger. Okay. Yeah, that's good. Okay, let's see what they got here. Oh, yeah. Okay. So here's the deal. There are things in organic called functional groups, and the way they work is that functional groups have a unique chemistry. They react in a characteristic way. All groups that are, for instance, alkyl halides react pretty much the same. All alkenes, all alkynes, etc. So these aren't the reactions, these are just the functional groups, and you just memorize them. And what usually happens is your teacher either says, memorize them all, or memorize this first half because this will be in the second half. Just depends on your teacher. So you can basically look them over and then see what happens in your class. But you're going to have to know them all eventually. Okay. Formal charges were great with, let me move this over here. Okay, let's see. All right, let's see if that'll do it. Yeah, I need this here. Okay. All right, that should be good. Okay. All right, let's see. Yeah, so here's the thing. These are really small things they're talking about here. So I'm just going to mention this. They're saying when we draw an oxygen like this with a negative formal charge, we don't have to put in the electrons, because if we understand how formal charge works, these electrons must be there. They
Mhm.
must be there because we couldn't get a negative charge that way otherwise. Because we have to give a complete octet. So they're just saying that this is this.
Uh-huh.
That's all they're saying there. Okay. All right. So what we did with formal charges is all displayed here. There's nothing new here. But what you might want to do this is done nicely. This is what I call simple, is you might just look over these and make sure that everything makes sense. But it's nothing that we haven't done. Especially because you did so well on that quiz. That's like, okay. I am impressed because I, I will tell you something. I won't tell you who it is, but I get a guy that every single time he just bombs every quiz, and he said, "I thought I knew it."
Oh.
It's bad, I know. And I said, "Well, it's not that bad, but you know, but it's terrible." It's like I'm trying to help him. And I don't know if he's that dumb. He's not. He's kind of lazy. He doesn't really work hard at studying. So I think that's the problem. Not that he's, that he couldn't do it. Okay. Yeah, I'm not seeing anything new here. But again, I do like this book, and it's worth looking at. Okay, three-dimensional bond line structure. Okay. So this we haven't done, I don't think. I went through the notes. We didn't do this. When you have a molecule and you draw a wedge like this,
Yeah.
that wedge is coming out at you. So what we're thinking of is we're thinking of this molecule where these straight lines here are sitting on the computer screen. And then this wedge is popping out. And this dotted line is going back. So essentially, whenever you have a wedge, this is going to be coming out. And whenever you have this hash line, this is going to be going in. And you can think to the screen,
I can't see some of what you're writing.
Oh, okay. I'm sorry.
It's
Yeah,
okay.
yeah. Just tell me, and I'll do it. Yeah. Okay. So what happens is out is going to be like this, and then in is going to be like that. So if we draw a picture of methane, which we've looked at already, what you get is you get this over here. See, there's our methane like this. And these bonds here are coming out, and the one in back is going in. So I've got different colors on here. I was working with someone, but let's just say that the hydrogens up front are the red and the blue. And what happens is the one in the back is here, and the one that's going straight up is the line over here. So from what you're seeing, you probably see the red over here and the blue over here.
Yeah.
Is that what you're seeing, or the other way?
That's what I see.
Okay, good. So that's how that works. Okay, and what happens is if we have a ring like this, and we're gonna go like this. See how we make the spatter on top?
I can't
Oh
see it.
yeah, I'm sorry. I usually make this smaller. Let me ask you something. Can you see the book? Because I usually do it like this. And last time you had a problem, and I'm not used to working this way, but I will. So can you see the book okay with the size or not?
Yeah, it's fine.
Okay, good. Then we won't have a problem with that. So this thing coming out like this is going to be popping out of the paper, so that if we take this and we look at these carbons like this, what we can do is we can draw it like this. And these carbons would be there and there. And they call this the bridge. The bridge. And so the bridge is popping up like that. And this is looking at it, we'll say, from the top. And then this is looking at it from the side. Does that make sense?
Yeah.
Okay. So that's another example of a wedge, but it's presented in a cyclic compound. Okay. Okay, so now they're going to be doing a whole bunch of things. Yeah. Yeah. So here's the situation. They did what I showed you here, which is great. And with this, in real life, these bonds are not in the plane of the paper, not both of them. If you build a model, they're not. But it's so nice to draw it this way that they draw it this way. So it's not completely accurate. But what's happening is this ring is going back. So this part's accurate, and this part isn't exactly accurate because the bond angle here is 109.5. So they can't both be in the plane of the paper, because that would be 180. So we draw it incorrectly because it's easier. And then there was a guy named Emil Fischer who did a tremendous amount of chemistry back in the day. And he came up with something called a Fischer diagram. And it turns out that it was adopted, and it breaks the rules that we have here. So what this author has done is he's actually showing you that some of these aren't perfect. But what happens is when we go ahead and do a Fischer diagram, this is called Fischer, it's convenient to sometimes draw molecules like this. And what happens is that these bonds here are popping out at you, the ones that are horizontal. And these bonds over here that are vertical are going back. But we don't represent it the way we would normally do. We represent it with all straight lines because it's easier for us. And we just remember that this is the case.
Mm-hmm.
Okay? All right. So that's kind of like a warning that the author has done here. By the way, this is called the Fischer. And then when you do it like this, then this is called the Hallworth. Hallworth. So these are just ways of depicting organic molecules. And then they have a cool story here that you could read, whatever. It's about drugs and stuff, how they make them. And yeah. Oh, okay. Yeah. It's a long story. All right. Okay. So we've already done resonance. But let me just kind of review. We haven't done all of resonance. We just did the very simple thing. But just as a review, what happens is you're going to have atoms. And it doesn't really matter what they are. They're just going to be atoms like this. And then what you're going to have is you're going to have p orbitals like this. And those p orbitals are going to overlap. And then over here, you could have a positive charge, or you could have a negative charge, or you could have a single electron. And what's going to happen is we're going to say that this is going to be an allyl, either cation, anion, or radical, which are these guys. And what happens is you basically are going to have two forms of this. And it will look like this. And then what will happen is if it's a positive charge, you'll have this. And then if it's a negative charge, it'll be the same, but it'll be negative. And if it's a radical, it'll be the same. But the way we represent them with curved arrows will be different. So with curved arrows, what we do for the positive one is we move toward the positive like this. And if you want to go back, you move it like that. And then what happens is if you got a negative, so we'll put the negative here, then what's going to happen is we're going to bring this in like that. So we're going to start from the negative, which will be 2 electrons on a carbon, and whatever else is just hydrogen. And then this will come out over there. And then that'll be our resonance that way. And we'll get this now. And then that'll be our, like that negative there. So there's a nice pattern to this. So what happens is these are the two most common forms of resonance. And then you have the radical. So if you do it with the radical, you end up with this. you go like this, and then you have a single electron. So the correct way to do this is to use what they call fish hooks. That means one electron. That's the fish hook there, and then there's the fish hook there, and there's the fish hook there. So that's going to give you this here, bing, 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 and then you'll have the electron there and there. And if you wanted to go backwards, you would go like that, and you would go like that, and you would go like that. That's a little messy, that one. Okay, let me fix that. So you would go like that. There we go. And there's one other very, very minor one where if you have a double bond over here, then what you would do is you would bring this up like that. So everything you do is going to be one of these. Uh-oh, I didn't mean to do that. Okay. And a positive like that. Okay, so now we've got the basics there. And I'm just going to put this in a box, and I'll put this in a box. Okay. And now we're going to show you a fancier resonance form. Let me see how far they go with this, as far as fancy goes. I want to do it, but it looks like he's keeping it really simple. Yeah. It's a good book to start with. Like, he doesn't blow you away. Yeah, he didn't really. Actually, I'm saying it's a good book, and I'm going to actually make it harder. But you just shouldn't have done so well on the quiz. That's why you're going to get this. Okay. So what we're going to do is we're going to put this up over here. So this will be an example of how you put these together. So we're going to start with this, and we'll put this here and this here. Yeah, that's good. Okay. I have to do it this way. Okay, good. Okay, so you get this on the test, and the teacher says, show me all the resonance forms. And what you do is you go, oh, well, which one of these is this? And you go, oh, I know, it's the one with the positive charge. So it's this one here. So if that's the one with a positive charge, then what we're going to do is we're going to bring these electrons in like this. So if we bring those electrons in like that, then there's going to be a positive charge on this carbon here, because that carbon lost one formal electron. That's why formal charges are important, because they're on resonance structures. So we get this, and then we get this like that. And then there's a positive. And then we go over here like this, same idea. And that's going to give us this here. So now we get this over here, and then we get an OH like that. And then what's going to happen is there'll be a positive here. And then what we'll do is we'll come over here and we'll say, oh, where can we go from here? I know we could drop these electrons down like that. And then if we drop them down like that, what we get is we get O, and now that oxygen has lost one formal electron, so it's going to be a plus like that. And then we'll have this, this, and this. And so that represents the resonance forms for this structure. Now, did that make sense?
I think so.
Okay, it's a lot, right?
Yeah, I've not seen any of it because the last time I saw a lot of stuff. This is all new stuff now.
Okay. Well, I wanted just you to have this because this is at the level you'll have on the test. This is what you'll see typically. We basically just did the real soft stuff here, the fundamental stuff. But I won't knock you over the head with it. I will tell you this. What this does for us is it tells us where the positive charge is located. So if we put these all together, then what we could do is we could say, well, as far as the positive charge is going to be involved, we'll make that red. There's going to be positive there. There's going to be positive there. There's going to be positive there. And so, and here. So when we look at the molecule, we can combine all of these so that what we have is we've got this oxygen here, and then there's going to be a partial bond here. And then there's going to be a partially delocalized system. That means that these are all going to be overlapping, and that the hybridization here is going to be sp2 because there's going to be a double bond located here. So that'll be sp2. That's the rule we had learned. That means that the entire system will be a bunch of p orbitals like this. So that's going to be p. And then the positivity is going to be over here. I want to use this color. BIM, okay. The positivity is going to be over here, and then over here, and then over here, and on the oxygen like that. So that's going to be called the hybrid. And the hybrid is all the resonance forms put together. And so when we're looking for how the molecule reacts, knowing where the positive charge is will help us decide how it reacts. And then one last thing, just to tell you, we are going to later on rate these as to which is more important or less important. And when we do that, the most important rule is the octet rule. So what happens is that when we look over here, and when we look over here, and we look over here, there's going to be 6 valence electrons. And that's not as good. But when we come over here, what's going to happen is this is going to have 8. And what we do is we say whenever something has an octet, that's the most important resonance structure, and there is no exception to that ever. So we can say that of all 4 of these, let's see, do I have 4? 1, 2, 3, 4, 5. Of all 5 of these, this one contributes the most to the actual structure of the molecule. Okay, if you didn't follow all of that, it's perfectly okay. It's just an introduction, and we'll come back to it later on.
By the way, how did you get 6 valence electrons?
Why does this have 6?
Yeah.
Okay, because there's a hydrogen here. So it's 2, 4, 6. These are not formal electrons. These are valence electrons.
Oh.
All of them, right?
Okay.
So when we're determining the charges, we use group number minus formal electrons, you know, that you have.
Yeah.
But when we're dealing with the octet rule, we're dealing with valence electrons.
Mm-hmm.
Okay, so the whole thing about drawing resonance structures is you're supposed to always draw them with the tail at the negative, and it's going to go forward. So this doesn't have to be positive here. It's just the tail has to be negative. It has to be electrons. So what would happen is if we were to start at the positive, that would be wrong because that's no electrons. By the way, the book we were using has the most complicated, really complicated explanation for about this issue that I'm pointing to. But what happens is resonance is all about pi. Resonance is all about pi bonds, not sigma. What that means is you never form or lose a sigma bond because resonance is only about pi. So you can never do that. So if you had something like this, let's see if I can create something here. I don't know if I can do it. I've seen it before. Let's see, one of these is going to work. Yeah, this one's going to work. Okay. If you did this, okay, then this would be wrong. This would, what I mean by wrong is it's not resonance. because that's a sigma bond. Does that make sense?
Yeah.
Okay. Also, there's some other rules that is atoms can't move. Atoms can't move. So essentially, everything has to stay in place. All the sigma bonds have to stay in place, and all the pi bonds are going to be drawn as moving. In reality, they don't move. In reality, it's the hybrid that represents the real molecule, and all the structures are just to help us visualize what that hybrid is. Okay, so don't touch a single bond. That's the rule. Okay, this is more arrow stuff, so you can look at that. By the way, I have 2 editions of this. This is the 3rd edition. Okay, so we're using the 3rd edition when you go and pick it up online.
Mm-hmm. By the way, do you know that organic chemistry is a second language book?
Yeah, that's by this author.
Oh, is it?
I know, yeah, Klein wrote it. I know I have not done any more than skim it, but a lot of the students I've worked with have sworn by it.
That's what I've heard too, yeah.
Very, very popular. Some people have shown me pages and I like them, but I haven't actually looked at the book. But yeah, I heard it's great. And if you want to get it, you can get it at, oh, did I give you a link to the place I'm getting these from or not? I don't think I did. I'll send you a link where if you want to get it, you can get it for free.
Yeah, my friend already sent me a PDF of that.
Okay, good, good, good. Well, I haven't heard anything about it other than good stuff. So, yeah.
Okay.
And this book is very good as far as, well, teachers don't always like it because it's simple, but they like the hard stuff. Okay, we have formal charges and resonance. There's nothing new about that. The one thing I can say though is if you have an oxygen here, and let's say that the oxygen has no charge, it's just like this. Well, let's say it has a negative 1, okay. And then you're going to be moving this. Oh, I have to make this work. Okay, yeah, that's good. Let's make that blue because I like that for pi bonds. Yeah, that's good. So let's just say that what you have is you've got an electron here and an electron here. And you want to figure out what's going to happen to the charge. If you swing this over, then this is going to be a loss of 1 formal electron. And of course, what that means is that the oxygen that you'll get here is going to have no charge. So it'll be 0. Now, there's 2 ways to do this. You can just calculate the formal charge in the usual manner, or you could say it lost 1 formal charge, 1 formal electron, so it's going to go up by 1. And most people do it that way, or they memorize the structures. So there's 3 ways to do it. You could use formal charge, you could do what I just showed you, or everybody eventually memorizes that oxygen with 2 bonds and 2 lone pairs is 0. After a while, it just becomes second nature to see that. And then you can memorize a lot of the other ones, like nitrogen that has 3 bonds and 1 lone pair is going to be 0. And then what happens is you can also start to memorize the pluses and minuses. And if you don't, eventually you will, because it'll go into your head and you'll go, oh yeah, I got it. But anyway, that's the deal. Okay. Okay, so some of this stuff that I did with you that was a little nasty, it looks like the author did as well. So this is kind of cool what happens here. You know, you're not supposed to make all these arrows go at the same time. You know, you're supposed to do them one by one. But you can do this if you want to demonstrate how resonance works. So that's what's going on here. They want you to draw they want you to draw the structure after all this stuff happens. And you're supposed to do them one by one. But if you don't do them one by one, this bond goes here, this bond goes here, this bond goes there. And that would be the result of doing 3 resonance structures. Does that make sense?
I think so.
Okay. So, I mean, here's the idea. most of the time, the rule is draw them one by one. But then when you want to demonstrate something to someone, you can do them all at once just to say, see, I don't feel like drawing them all, but this is what the result will be. Organic is very sloppy. The rules are broken all the time. What's really bad, though, is the language has been adulterated. So the rules for what something means have changed so that they have multiple definitions, meaning like different things. And it's like not a good idea. But anyway, um, here's what we'll do. Okay, we're going to start off. Okay, yeah, I'll show you what we'll do if we do it one by one. If we bring this over here like this, the next thing would be that would come over there like that. So then what we would get was we would get that. And then you would have this. And then you would have this. And then you would have over here like this. Does that much make sense? It doesn't. Okay. That's okay. So if I bring this over here, I have to move this. The reason I have to move this is I'll have more than an octet. Because
Okay.
there's a hydrogen over here. So I have to move this over to here.
Mm-hmm.
And that gives me this.
Okay.
Then, so this is what is kind of inside here. And then what we could do is we could bring this over like that, but then I have to move this over to there. And we get this. And then we get over here. And then we get this and this. Now this will have a negative there, and then this has a negative all the way through. We just didn't draw it in. And then this will be a positive like that. So basically they were asking you to go from here to here without drawing this.
Okay.
Okay, you're going to practice this and you'll become an expert.
Okay.
Okay, but these are good to practice on here. These are good problems. But yeah, it takes a little while. Let me explain something interesting about this. If you think about it initially, it's fine, but eventually your brain just catches it and it becomes second nature, and you can do it without thinking. You could talk to somebody with a regular conversation. You can do these structures. And the reason you can do it is these are visual and you're talking in words, and your brain has already learned this. And it's not just me that can do this or you that can do this. Everybody can talk and do resonance structures eventually because they do them so often that they become second nature. So you should understand that it gets easier.
Okay.
But don't talk to anybody while you're doing them now. Okay. Okay. I've seen professors that they're working on the board and they're talking and they're just two different things. And it's like, it is impressive when you see it for the first time. Okay. This is all the same stuff. So these are a lot of good examples. You don't have to go to the back of the chapter. These are all like in the chapter here. That's the one we did there. Okay. Okay. Yeah, this is all really, really good practice. Okay. So this is new. Yeah, this is new. Okay. How far is it going to go with that? Not far at all. Okay. There's a molecule called benzene. It's C6H6. It's got one ring and it's got 3 pi bonds. And what happens is it can be represented like this. And when we do that, we end up with this. And if we represent the molecule with p orbitals, we have p orbitals everywhere around the ring. And they each are going to have a single electron in them. And they overlap above the ring and below the ring. So what we essentially have is a donut above and a donut below the ring like that. And so this resonance structures here are representing the double donut because all the p orbitals are overlapping. And that's what's represented here. And it turns out that 2 chapters in this book is all about this molecule and its derivatives. So it's important, but that's as far as the author is going here. Okay. Okay, all this is good practice. This is the one I left out. I did all these other ones, including the radical one. This one here is similar to this one. So this is one I didn't do, but it's not anything significant. But anyway, this section here is a good one to look at for the different types of resonance structures. I'm going to throw it in because, okay, so if we have something like this, and we have an oxygen with a lone pair like this, that drops down like that. And what you end up with is the double bond here, and then this will be the oxygen with a positive charge like that. Yeah. Okay, so this was the added resonance form. Okay. Okay. Good, we got time for this. I wasn't sure if he would do this now or later. He's doing it now. So here's what we'll do. There are a bunch of rules to determine what's going to be more stable. We've learned one of them, the octet rule, is the most important rule. As you go through the book and you learn about stability, you add these rules on to resonance. So we start out with very few rules, 3 rules. And then as you go on, you add rules. Like if they say an alkene is more stable with R groups attached, alkyl groups, then you add that on. If they say a ring is more stable when it's 6 rather than 5, you add that on. Okay, so the way it works is we're going to start with 3 rules and then you're going to add them on. And they're not going to list them for you. They're just going to add them in each chapter and you're going to have to remember them or I'll remind you of them. Okay. But that's the way it works. So then you'll do a resonance structure. They go, why is this one more stable? And you go, oh yeah, remember back in chapter 5 when we told you this? You don't remember that? That's how it goes. But you'll get used to that. But for now, it's going to be pretty nice. So what we're going to do is I'm going to just give you 3 rules here. Okay. Let me do this in a way that will be easier to do. Okay. Okay, that's a good way to draw. Okay, so now what I'm going to do is I'm going to do this. Yeah. And I'll get this here. Okay. So this is like this. And then this will be like that. And this represents here. Okay, this is my system for explaining it all quickly. I kind of try to develop something that would work here. And then this will be like this. And then this will be like that. We can go that way. Okay. Okay. So these are the different residence forms. So this one has all octet. That's the most important rule. So these rules are going to be listed in order of importance. That means that there's two rules and one happens and the other doesn't happen. And then in another molecule, it's reverse. The one with the rule on the top wins. Did that make sense?
Can you repeat that one more time?
Sure. It's a hierarchy of rules. If there's a competition, the rule that's higher up on the page wins.
Okay.
Okay, so this is the best rule. So this has an octet, and this over here, this is going to have 6. And this is going to be 6. So this one wins because of that rule.
Mm-hmm.
The next rule, okay, so that's number 1. Then number 2 is going to be positive and negative separation is bad. So what happens is you see how this is positive and negative here, and this is positive and negative here. If there wasn't the octet rule, these would still lose because they have charge separation. Is that okay? You love this stuff, don't you? Yeah, well, what can we do? It gets better though, because this is just a bunch of rules and stuff. It's not, this isn't Orgo yet. Okay, and then the next rule, so I promised you 3 rules. The third rule is negative on electronegative, positive on electropositive is good. So that allows us to differentiate between these two. Here we've got negative on electronegative, more electronegative. And here we have it on the positive here. You could do it with the carbon as well. So what we have is we have 3 rules. So this one example demonstrates all 3 rules. The octet rule is the number 1 rule. The charge separation is the number 2 rule. And the negative on the electronegative is the 3rd.
Okay.
So, this covers a lot actually. Okay. So tell me what are you a little tentative about this? Because I'm. What are your thoughts?
I mean, like everything we learned today was new information, so I probably need to study a little bit more just to understand.
I'm throwing it at you quickly, but I'm counting on you to work with it. By the way, this is the time where you really do need to do the practice problems.
Yeah.
This material here we've kicked it up a notch. So you definitely need to work it. But I don't know, if I'll give you a quiz on Thursday, and we'll see how it goes.
Okay. There are practice problems in this book, right?
Yeah, there's plenty. I think I would stick with this book. If you find out that this book is too easy, the other book will have harder questions.
Okay. Is there an answer key to both books, just in case I need to check?
Okay, here's what I'm going to do. I'm going to send you the link to where I got all this stuff. You just have to do a search, and you'll find the answer keys. You can get those free. Just their links also. So yeah, there are answer keys. So when you do the search, though, it takes a little while sometimes to mess with it. Like sometimes if you give it too much information, it doesn't find the book. If you give it less, like the author, the year, solutions manual, I find is better than if you give it, the edition and the publisher and all that. I just keep it simple, and it usually gives me the answer on the first page.
Okay.
So I'll send you that, and you can find those, those two.
Okay. Okay. Thank you.
Okay, you bet. See you later.
Bye.
Bye.